Ladies and gentlemen, Redis geeks and geekettes, welcome to Redis Day.
Hi everybody, thanks for getting up today morning and come here in big number. And today I'm going to do something different compared to my normal talks because this will be a live session where I will try to mostly show you the new Redis data type that's called the stream, and it will be basically the big feature of Redis 5, version 5. That will be released like in a couple of months if everything goes well. If you ever used Redis, you know that normally it's very simple to interact with the Redis data types. There are basically commands. You call such commands in the context of key names and some operation is performed. Streams is like that, but it's a more complex data type compared to the one that so far we introduced in Redis. It's also the first new data type after many years because it's true that in the previous years we added something like hyperlog logs, but those are very specialized data structures that can solve a single problem. Can I ask to retain my eyesight? So basically, thank you. The stream is the first general purpose big data structure that's introduced to Redis after years, and it's the most complex ever. But fortunately, the API of streams is like composed of 3 different floors. So you can learn it depending on what you are trying to do. The first one is basically the data structure itself that's like a log file. You can imagine the stream is like a log. You append to the streams and something happens. The second part is the blocking API. And the third part is the consumer groups. That's a concept that we got from Kafka, but executed in a quite different way in the context of Redis. So to start, we execute a Redis server. This is the consumer groups branch is public, but it's not still merged into any stable release. So in order to use what we will show today, you will have to wait a few months. OK, let's show how it works. We deleted everything that was inside the database, and we can start with the most basic command of Redis, which is used in order to append something inside the stream. So we use the xadd command. Xadd, like most Redis commands, will take the key name, my stream, and then I will use I will append the data that I want actually to add inside the stream. And normally, for example, if you know Redis lists, a single element in a Redis list is a string. However, streams are different. Each single element in a stream is actually a key value, key value, key value pair. It's like if elements are composed of small hashes. Like if it was, I don't know, a JSON object or something like that. Because many times when you want to log something, you want to have multiple information. Think at a command separated file. For example, a command separated field file. You have, for example, the client ID, and you have the temperature, and you have the, I don't know, the humidity. Often time series, for example, are generated having multiple fields. So this concept is directly inside the streams. So I can say, for example, that I am, imagine that I am a weather station and I'm adding data. So I say that I am station 999, station 999, and temperature is 20 degrees. Oh, but we are in Tel Aviv, so it's 28. And the local time where this data was generated is like this Unix time and whatever. But I cannot use my own stuff, so OK. I have to add this asterisk, and we will show shortly why this is needed. OK. When I call this command here, what happens is that I receive the ID of the new item just added inside the stream. And this asterisk here means auto-generate the ID for me, because I could specify also an ID if I wish to do so. But normally, it's much better if we let Redis generate the ID of the items. So what is what's basically the feature of this ID? This ID is guaranteed to always increment. So new entries will have always incremental IDs. And after all, if you think about it, we are appending, so we want such IDs to be incremental. What you can do with these IDs is to take ranges, for example. But this ID, as you can see, is a bit odd in the format. It's two fields. There is one thing that looks like a timestamp, because it is a timestamp in milliseconds. And then there is this 0 there, because this is a sequence number for the items that are generated in the same millisecond. Otherwise, if multiple items are generated in the same milliseconds, we would have like the same ID for multiple items, and this is not good. So we have this concept. We can add a new item. For example, this is station, I don't know, 995. Temperature is 27 degrees, and the local time is a bit different. OK. And a new ID was generated. Because the millisecond time is quite fast to advance, of course, we see that the sequence number is still 0. But if I wrap qxadd in a transaction and execute both the statements will be executed really fast, so that they will be executed in the same millisecond, very likely, and we see how the sequence number increments. However, as you know, basically, in every system that you design, you should never rely on the local computer clock, because it can jump backward, forward, so it's quite unreliable when you want to generate something that has the guarantee of monolithically increasing again. So what we do basically is that if the top item of the stream is greater than the current time, then we use the time at the top item and just increment the sequence number. Because the sequence number is 64-bit, you can add all the items in the same timestamp if you want, because 64 is much more than the computer memory, because if you have 64 bus, you cannot add more memory than 64 addressable memory. OK. The way I can consume this stream is using the xrange command. For example, I want take from my stream from the minimum to the maximum element, and this will dump all my data. But I also could specify that I want just 2 items, for example. Here I used the minimum and maximum possible IDs, but I can specify instead an ID. I want from here to here, and this is just a single item. So the first thing I have here is range queries for free. And the interesting thing is that since the IDs of the streams items have this concept of the time, range queries are automatically, if you want, queries about time. So if I want to understand in a given 5 minutes range what my weather station, what was the output of my weather station, I can use that in order to get only that. So based on what we said so far, we can write a producer program. This is Ruby code, this very simple Ruby code. So I create basically here a new Redis object, and I give this station a station name It's just station and the process speed. And I start with a given temperature. And then at every loop, the temperature will be changed randomly. And I will perform an XAdd in the temp key. That's my stream. Auto-generate the ID for me, and use a station ID, station name, and the temperature is the temperature that's it's changing. Okay, let's try to execute this producer. Okay, it works, it doesn't produce any output, but I can, with xrange, check what's happening. Okay, actually, it is generating new symbols. As you can see, the temperature changed always because of the random number generation and so forth. I can use also xlen to see how many items there are inside my stream. And because I add one new item every second, I see this number increasing. However, while xrange is interesting if I want to inspect my stream in a given range of IDs or of time, if I wish to use time, because the IDs are time-related. Imagine that I want to consume this stream in order to do something different. For example, a use case would be I want to consume the stream with a worker, because if the temperature reaches 30 degrees, I want to notify with a message my users, because it's too hot or something like that. In that case, the range query command is not the good one, because imagine you have to take always ranges. It's like polling, then again, so it will be terrible. What we need is a way to consume our stream, and if there are no items greater than the one that we specify, we wait. Otherwise, when items arrive, we get these items returned, and we can continue again, specifying in this command what's the latest ID of the item that we consumed, the greatest ID of the item that we consumed. Let's try this. For this, I use the xred command. So I say xred, my stream name, that's temp, and I specify my streams, because this command is able to consume at the same time multiple streams. Maybe the same worker is interested in multiple different events, and that if the xred command would not have the ability to query multiple keys at the same time, you will need to create two threads with two Redis objects. So it's very important that it is able to do things like that. My stream is called, streams temperature, and I have to specify for each key what is the maximum ID that I already have. For example, I can see 0, and this ID is the lowest possible, so I will see that it will return everything, all the items that are inside the stream. Here I can also use a count in order to limit the number of outputs. But it's more interesting the fact that I can use this special ID, $, in order to say, give me only the items that will arrive in the future compared to the time when I'm connecting. And nothing new is arriving in this very short moment, so xred returns. And I can finally introduce a new option, that's block. I want to block for 5 seconds. This is in milliseconds, so I wrote 5,000. And I want 5 items for the stream, and I want only the new items. Remember that in this moment, we have a producer that's producing 1 symbol every second. So if I try that, eventually, I will get something back. And normally, the second call that I do, I substitute the $, with the highest ID of the item that I already received. So I will get all the others. And again, this is the last item that I received. So I use this ID. And in this way, I can consume all the stream. When I am too fast and the producer is not producing more items in order to serve me, I block, and then everything continues. What happens is that if I stop the producer here, and I wait again for the new items, the command will time out after 5 seconds and will return nil. So based on this new knowledge that we have, I can write finally a consumer for the stream. This is the simplest consumer that we can write. So we start with a last ID that's $, and in an infinite loop, we perform xred command, blocking for 2 seconds with a count of 10, and the streams is the temperature stream with last ID that starts as $, but then if the returned items is nil, then there was a timeout like I shown you. And otherwise, I iterate the items returned. Note that this is an array of array because each keys that I queried is returned as a different array. So I want x index 0 because I have a single key here. And the first element of index 0 is all my items. And I get the ID and the fields, and I put the ID of the item that I'm consuming at its fields. And here is where I want to update the last ID. Note that I don't check if the last ID returned is the greatest that I have so far, because items in the stream are guaranteed to be returned already in order with IDs that are greater and greater. Okay. So we can start again our producer, and finally we can start our consumer. And our consumer is consuming items as they arrive. However, there is a problem with this example consumer that I wrote. If I stop this program and I wait for like a few seconds and I start it again, I'm missing all the items that were produced while the program was stopped. In some kind of applications, that's okay. But in other applications, I do not want to miss messages. So I can refine my code, and I can write a new version of the consumer. This time, I want to use a file in order to store the latest ID that I saw so far. So this is the file name where I store the ID. This time I abstract the message processing. I just put, as I did before, but this could be anything, like a very slow computation, or just check if the temperature is greater than 30 degrees, whatever you want. At startup, I check if I have a last ID file. If I don't have, I start with $, saying, okay, it's the first time, so give me just what you start to produce starting from now. And then the loop is the same. I read, there could be a timeout, so I continue again. Otherwise, I just process the message, set the last ID, but this time I write the last ID to the file. Let's try to execute this second consumer. No, sorry, there was already a consumer to ID. I deleted it. So the first time it will just start consuming the new items, because if no file was found, $, was used as the next ID. This time, if I stop this program and wait for 10 seconds, we will see that when I restart the program again, the program will consume immediately all the items that it missed during the time that it was stopped. And I could remove again the consumer ID and change my program so that the policy is when the consumer is started, as in initial ID, you use 0. In this way, I change the semantics and I say, when you start, you consume all the history, and then you start for to wait for new things. Let's try our new program now. And yes, I consumed a lot of messages because they were all in the stream already, and then it starts to consume the new stuff, as you can see. So far, so good. But there is still interesting things that I can do. So imagine that, the interesting thing about this program is that while I have, for example, a consumer running, I can start another copy of the same program. And both are consuming the same items. For example, here, temperature was 25.290, and here is 25.290 is the same item. So this is the first interesting thing. In Redis so far, you had no way to consume with multiple consumers the same stream. You had or pub/sub, publish subscribe. In pub/sub, you can do fan out, but there is no storage. It's fire and forget. There is no way to recover the history of publish subscribe. Otherwise, you could use a blocking list. The blocking list is the problem that if you block, the first client gets served with an item that's removed from the list. The second time will be served with a different item. So you have no way to basically fan out. In this way, I can fan out. However, I could have one problem. Imagine that our items are not weather station items, but are prime numbers. And I want to factorialize these prime numbers because I want to break some kind of encryption. This way, the time in order to process each message becomes very long, because to factorialize a large number is a slow process. So I could say, for example, I want to factorialize all the prime numbers I'm receiving, but I don't want to do it with a single worker. I need like thousands of workers working in parallel, each in a different message, so that they can cooperate in order to make this work much faster compared to what one worker alone could do. I have to introduce the new concept of consumer groups. Basically, a consumer group is an abstract consumer that consumes all the items and then provides different items to different workers. And this is implemented as an extension of the API we saw so far. Okay, so I have still my producer. And the way the consumer the consumer groups work is by using the xred group command. The syntax is similar, but I have a mandatory group option where I specify a group name. And I have to specify what's the name of the consumer that is asking new items. So inside a consumer group, each worker has a different name. The name is just a string. I can say that I am Antireds, and my streams are temp, and my initial ID is this special ID. That means give me just things that were never provided to other workers. Okay? Okay. The problem with the consumer groups is that the consumer group must be created before to be accessed. So I can create the consumer group using the xgroup command. So xgroup, my group, create xgroup, create temp my group. I don't remember the syntax, but I have a magic way to understand how to do this. Okay, it's xgroup, create key, group name, and I have to specify the starting ID, because the groups that will use this consumer group, what should get? All the history, or starting from a given item, or only the new things? Okay, the producer crashed at the same time because I stopped the server. So xgroup create. The stream is temp. My consumer group is called my group, and my starting item is $. So only the new things I want to be consumed by this consumer group. At this point, this command should start to work. Exactly. Okay, this is interesting. What happened here is that in the context of this group, I read all the new items that were never provided to any client in the consumer group so far. And I can do this again, and I will receive only new items, okay? And here I can also block, as I used to block previously, okay? And this works like that. Okay, now there is an interesting thing about this. If I use as ID 0, or any ID that's not greater than, I will see only my history. If a given item was provided to this consumer called anti-reds, the history will be local to this consumer. Even if I ask for a range, I will have visibility only of things that were provided to me. So I can use this command, and I will see again and again the same 35 items that I received but I did not acknowledge. Because when you are inside a consumer group, you have to acknowledge that you actually processed a message. So for example, I want to process this message. And when I processed the message, I have to use x acknowledge in this stream, in this group, and this is the message that I acknowledged. Okay, now the stream knows, the consumer group knows that this message was really processed. Because one thing is to provide a message to a worker. One thing is to be sure that it was processed, because the worker could crash immediately after receiving the message, for example. Or it's too slow, so still cannot process the new message, and it's stuck in the first message that it received. Now that I acknowledged this message, if I try to read again the history, I will see that this new message that I acknowledged is missing. Now are 34 instead of 35. Okay, so let's write a new version of my consumer group. This is consumer 3 and use a consumer group. 5 minutes. Okay. So my consumer group name is given by the first argument to this program. And I use again process message. If the file exists, I start with my ID. Otherwise, I use as ID 0. And everything is the same, but just I call xred group here. And I process the message. This time I acknowledge the message, and I write the new ID. So let's call this program. Let's execute, and this is consumer 1. And okay, so far it is exactly like the previous example, but now I use a new one, consumer 3, and I start a new consumer. As you can see, this will start to receive messages as well, but the rate at which the new messages are arriving is 50% compared to previous one, because one worker is receiving one message and the other worker is receiving the other message. The xred group guarantees to be fair. So if there are many consumer groups, the first that is arrived is the first served, and so forth. And now what you can see is that if I stop one consumer group, the other one will start to see messages again once every second. Okay? However, sometimes it happens that we write very bad code. So what could happen is that after the message is processed, but before the acknowledge, I have a software bug here. That's quite a bug. So I start again this program, and unfortunately it crashed. Imagine that this worker will never recover again. What I need is a way to understand if there are pending messages in my consumer group and potentially reassign such messages to healthy consumers. The expanding command does exactly that. So expanding temperature, my group, and I want all the pending messages, so all the IDs, and I want to show up to 100 messages, and those are all the messages that are pending. As you can see here, it's the messages that the consumer consumed but was not able to acknowledge. And I here can see the idle time of such message, how much time it passed since the last delivery attempt to some consumer. And this is the number of times we tried to deliver this message without success. So basically, what we can say is that the Stream fundamental API, if you want to do time series, is a simple one. It's just an append log, and you have ranges on top of that. Then if you want some more powerful, you can use the blocking API. And using such API, you can create different topologies where workers are consuming this stream. And then you can say, no, I want more. I want, it's a more complex API, but I want the ability for the server to track what message is processed and what message is not processed. And so you can use the consumer groups. Another thing that's great about the streams is that the memory usage is extremely low because it uses an advanced representation where we use a radix tree, and each radix tree, instead of having a single node, a single item, it uses a blob that encodes multiple items, like in a linear blob of text. So it means there are less pointers. We can exploit the fact that stream IDs with the same fields will be compressed. The IDs will be delta encoded. So I believe that this will be a quite interesting feature for Redis. And in 2 months, we have in GA so that you can use it for your use cases. Thank you. Thanks.